What the kernel is?
Yeah.
Yeah, so if we have, a linear transformation C, it goes from some vector space to some other vector space, right? So, the kernel of T is equal to all of the elements in the domain such that the transform takes them to 0. So if we look at, this is U, this is V, and we have some elements that go to 0. Of course, it's a linear transformation, 0 will always go to 0, right? The question is, does other stuff go to 0? So in this example, we might have a vector A and a vector B. They all go to 0. And this is analogous with the null space of the matrix. So that T is defined by taking X to AX, where A is a matrix, and the kernel of T is equal to the null space of A. So whenever we can write the transformation as a matrix, they're exactly the same thing. It's just in other situations where we can't. Specifically when it's well, we'll kind of talk about that today. When these are infinite dimensional vector spaces, we can't write them as matrices. We can write the transformation as a matrix. Let's start the camera. Looks like it's on. Okay, cool. So, yeah, I kind of squeezed that in at the end of last class really quickly. So today we're going to go further with talking about stuff with bases. That's the plural of bases. 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 Just like matrices. Okay. So what can we do with a basis? Well, okay, so first of all, let's say that we have a vector space V. Has a basis. We typically, that looks more like a beta. I'm just writing capital B. They usually do it in like a cursive writing, but I don't remember how to do cursive. V1 to begin. Okay. So suppose this vector space has this particular basis, and we know that every V in our vector space can be written as a linear combination of V1 to Vn. This is part of the definition of a basis, right? It's V is spanned by these vectors. So these are all elements that are inside V, and if we take all the linear combinations, then we recover the entire space V. Okay, so anything can be written as a linear combination. What makes a basis special is that it can be written as a linear combination in a unique way. So we need to be able to demonstrate that this is true. So let's take this V, let's say, it's gotta be written as a linear combination because it's in the span. So let's say that linear combination is A1, B1 plus A2, B2, and so forth up to A and Bn. Now, if we pick any, I want to be careful how I choose my words. Let's say that I can write the linear combination also like this. C1, B1 plus dot, 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 plus Cn, Bn. I'm trying to avoid writing it as a different linear combination. I'm just going to take two linear combinations, two general linear combinations. What I want to be able to show is that these two are actually the same thing, that A1 equals C1, A2 equals C2, and AN equals Cn, right? It should be a unique, that's what I want to show. So the most common way to do this is to subtract one from the other and show that we get 0 for each of these weights. So if we subtract one from the other, we get B minus B, which is 0. On this side, so B is equal to this and B is equal to this. So subtract B from B, I get 0. On this side, I subtract this from this. And because of all of our special properties of vector spaces, I can collect the weights for each vector. So A1, B1, let me write it out like this first. A1, B1 minus C1, B1, A2, B2 minus C2, B2, plus dot, dot, plus AN, BN, minus CN. Right? I've just taken the first linear combination and I've subtracted the second linear combination from it. So just by rearranging terms, I can say this is A1 minus C1 B1 plus A2 minus C2 B2. I'll get out of the way in just a second. I'm probably blocking it for someone on the other side of the room here. AN minus CN. Is it clear what I did here? Right? I just collected like terms, basically. That's all I really did. So this is A1 minus C1, A2 minus C2, and AN minus CN. And what we've arrived with, where we've arrived at the end, is that we have this linear combination right here of our basis vectors equals 0. So the fact that they spanned our vector space was only half the definition. The other half was that they're linearly independent. Which means that if we have an equation like this, then each of these things has to be equal to 0. In the old way of writing this, all these things have to be 0, right? So in other words, AI equals CI. I'll write a little square to indicate that we're done. So that completes our proof. So if we have two linear combinations of the basis vectors that give the same element, they have to be the exact same linear combination. Right? All the weights have to be the same. The book, did they give this a special name? Yes. They call this the unique. Yes, I write my cues like this. It's too late in my life to change it now. Unique representation theorem. The unique is clear, we just proved that. The representation. What do we mean by representation? We mean that if we take anything in our vector space, we can represent it as a linear combination of the basis vectors. In essence, we can take anything and we can rewrite it as just a list of numbers. So we're going to introduce a special notation to show that we're doing that. So we have any element in our vector space X then we can represent it relative to our basis B. Any basis, as long as we have a basis for the vector space, we can represent it relative to the basis in a unique way as, this is how we're going to represent, we're saying this is the representation relative to B. Okay? We represent it as this column vector. And this column vector is, of course, an element of Rn. Maybe I should write B is equal to B1 to Bn. That was our basis. This is a set of vectors that we've given some kind of ordering. Right? We've said this is the first one, this is the second one, this is the third one, and so on. Now, with that, what we can say is that, maybe I should make an effort to, no, forget it. I'm writing my B's like this, we'll figure out how to write B's in a different way later. So, if we have this particular representation, what does this mean? It means that X is equal to C1, B1, and so we call this a, what does the book call it? Coordinates. These are the coordinates of X relative to the basis B. So this list of numbers. Remember, the elements of Rn are just lists of numbers, right? So we call this the coordinates of X relative to B, or simply the B coordinates of X. Example. Write that in this little corner here. Give it a shot. So let's look at a couple of vectors in R2. We're going to suggestively name them B1 and B2. 1, 0. And what's the other one? The book uses 1, 2. Let's use negative 1, 2. No copyright strikes. So first of all, is this a basis for Rn? Is that a thing that's easy to see, or does it take work? It is not a basis for Rn? R2? Excuse me.
Well, yeah.
What, you're saying yes?
Yes, it is a basis.
Why?
Because, well, I was thinking at first of the 1, 0, 0, 1. But
That is
then if you reduce it.
So you're saying we're reducing a matrix?
Well, yeah, like you could, if it was a matrix, you would take the 2 eliminate the negative 1. So it would be a basis, right? Completely.
Well,
And it's linear.
let's write it as a matrix first, so we don't have to just imagine what you're talking about. 1, 0, -1, 2. We have the benefit of pencil and paper, board and chalk. Now, how would I tell if it's a basis by looking at this matrix?
The columns are linear.
The columns are linearly independent. And how do I know if they're linearly independent from this?
There's a pivot to each column.
Yeah, so, well, first of all, this is definitely a pivot. And we move to the next column, or we move to the next row, and we go to the first column with a non-zero entry. I got that. And then if we continue row reducing, we would do more stuff, right? We would eventually get to the point where we find that's row equivalent to 1, 0, 0, 1. Is the idea of the matrix. So that was one way of telling whether or not a collection of vectors was linearly independent. Stack them into a matrix, do the row reduction algorithm. If we have a pivot in every column, then they're linearly independent, right? Anybody know an easier way? Andrew, you've already answered. I have to pick on somebody else. Who wants to be next? Yeah, exactly. For two vectors, there's a much easier way to tell if they're linearly independent. Now remember, a lot of people were mistaken about this on the first exam, so I want to emphasize this. This is only a test whenever there are two vectors. When there are more than two vectors, then just looking to see if one is a multiple of the other is not good enough. We have to find out if one of them is in the span of the other ones, which is a much stronger statement. Okay. In general, we could do something like this. Row reduction is a very efficient algorithm for figuring out if they're linearly independent. In this case, though, we could just look and say that, you know, this is a 0 here, and this one doesn't, so we can't do that. Okay. So first of all, this is a basis. So we'll call it, continuing with our maybe not so great naming convention, B, capital B. I could have called that matrix capital B, and then this one could have been cursive B. Too late for that. Okay, so suppose we have a vector, and its B coordinates are, I say minus 2, 3, let's go 2 minus 3. Mixing it up. So what is x? What is x? Don't say the 24th one or the alphabet.
It's, would it be 2 times B1 minus 2 times B2?
Yeah. So this times this plus this times this. Just to emphasize it, I'm going to write it like that. So what do we get from this? We get 2 times B1. That's 2, 0. Plus negative 3 times this is 3 minus 6. And so we get that x is equal to 5 minus 6. So it's pretty straightforward to take something in its coordinates. As long as we know what the basis is, we can take the coordinates and convert it back. Now, I want to point out another way that we could have done this. We took 2 and multiplied it by this column. We took negative 3 and we multiplied a SID column. I'm giving away the punchline. 2 times this vector, negative 3 times this vector, and add them together. This is exactly what we do when we do matrix multiplication, when we multiply a matrix by a vector. Take these to be the columns of the matrix, this to be the vector, and what do we get? We get, I'm going to squeeze in here. I hope you can see. You can't see this, I'm sure. Let's do it here. 1, 0, minus 1, 2. And then 2 minus 3. And this matrix multiplication, of course, gives us the exact same thing. 5 minus 6. the basis, it's kind of a nice basis. 1, 0 is the first entry. 0, 1 is the second entry. And I'm writing this as a set. Really what I should be doing is giving these names that indicate very clearly that they have an order, right? A set doesn't have an intrinsic order. We write things in a particular order, but that doesn't have anything to do with the set. I want to indicate that this is the first one and this is the second one. So if x was 5 minus 6, is that right? This example doesn't really matter, right? What would be its representation with respect to, let's call this E, over E. What are its E coordinates? So how do I find the representation of this thing with respect to this basis? I want a linear combination of these two things. I'm gonna get someone else. You've only answered once today, Dave, but you're still, you haven't filled your quota yet. So let me just remind you that what I want is something times 1, 0 plus something times 0, 1. This is what we're looking for, right? Something times this plus something times this gives me this.
You need to augment the matrix.
I could. Let's try that out. Make a little room. I'm just getting the erasing out of the way. I'm not trying to build suspense. The augmented matrix. Ah, right. So we want, what we're ultimately doing is we're trying to solve an equation. This equation right here is exactly the same as the matrix equation, 1, 0, 0, 1. C1, C2 equals 5 minus 6. The pace I'm going right now, I'm definitely not going to get through all the material today. When we have a matrix equation, we can always solve it, or find out that it has no solutions, or find out that it has infinitely many solutions, by making the augmented matrix and then row reducing. And this is an important skill for this class, which I am unfortunately very bad at doing in front of a bunch of people. So, maybe a lesson for me to learn there. But I've got something working in my benefit right now. How much do I have to do to row reduce this matrix? Absolutely nothing. So I get my solution straight out of this. C2 is equal to -6. C1 is equal to 5. And so I get that the representation of 5, -6 with respect to the standard basis is 5, -6. So that's another reason why we like the standard basis. If we look for the coordinates with respect to the standard basis, we find that we've already got them. Right? A vector in Rn has the coordinates, has the E coordinates, has the standard coordinates, whatever it is already. So it actually doesn't change it at all. So this transformation from a vector to its coordinates in some Rn, this Rn being however many basis vectors we need to multiply by weight. Right? We need that many numbers. That transformation gives you something in Rn. In this case, the basis had two things, so it was R2. And for the standard basis, that's sort of like, we've almost gone in a circle. We defined R2 as just lists of two numbers, while Rn is just a list of n numbers. And then now we're treating it as an abstract vector space, and then looking at how to represent that inside Rn. Well, if we just use the same old representation that we started off with, we find that, we get back to right exactly where we started. So that's kind of interesting. The book has a nice section here on the graphical interpretation of coordinates. I'm going to totally skip that. Although it is interesting, and I do recommend that you read it. So going back to this equation right here. So this one. We solved it by row reduction, but we actually could have done something, we could have done something even much simpler. We could have just noticed that this is the identity matrix. And so whatever I put in here is gonna just come right back out. Somewhere in between the level of complication of row reducing something that's already row reduced, and noticing that we don't have to do any work at all, doing just a little bit of work, multiplying both sides by the inverse. Well, if I multiply this side by the inverse, let me take one step back. If I multiply this by this, I just get this. So ultimately, what I could have done just in this step was I could have just said C1, C2 is equal to 5 negative 6. So let's pretend that it wasn't something so simple. Actually, let's not pretend. Let's go back to this example and see that we can actually. Well, we already have a matrix here that's not already row reduced. I have room right there. I need more room. So we have a basis. B1 is equal to 1, 0, B2 is equal to, it doesn't really matter if I do the same thing or not. Minus 1, 2. And we said that the representation of x was 2, negative 3. Right? Let's take 5, negative 6 and work our way backwards. Instead of giving you the representation and trying to figure out what the original vector is, let's take the vector and try to get the representation. That's exactly what we did here, but we did it in an easy case, simplified case. In this case, it's not so easy. 1, 0. If I form, let me be very clear about what I'm trying to get. C1, D1, C2, D2 equals x. Maybe I should actually write it out. C1 equals 0 plus C2 equals 2. I've just filled in the things that I already know. C1 and C2 are what I'm trying to figure out. So this is really the same as a matrix times a vector equals a vector equation. The matrix is first column 1, 0, second column minus 1, 2, times the unknown, C1, C2. You can see how this, why we call this algebra, right? We've got equations in terms of unknown variables. It feels like we're back in, when did you learn algebra? 3rd grade? 4th grade? We're back in 4th grade, except there aren't numbers anymore, they're complicated things. Vectors and things. And what do we do in those situations? When you first saw 2x equals 4, you never thought back on this and thought, this is so easy now, it's like you don't even have to think about it, right? To get the answer to this, you know that divide both sides by 2 and you get x equals 2. The equivalent thing to do in a matrix vector equation, well, we can't divide by a matrix, but we can multiply both sides by its inverse, right? So one thing we could do here, well, we could do what we did before, or what we started to do before, and then found that we were already done. Was we could write the augmented matrix, go through the row reduction algorithm, find that, well, we know that row reduction algorithm will finish because we already know that these two columns are linearly independent. So we know we're going to get an answer from that big long theorem of all the various equivalent ways to say that a matrix is invertible. The other way is that we could just invert this matrix directly. If I remember how to do that, how do I do it?
I did have a question real quick.
Okay.
If we wanted to be like silly complicated,
Yeah.
couldn't we also use Kramer's rule?
Kramer's rule actually will be equivalent to inverting the matrix. So what are we doing with Kramer's rule? We're replacing one of these columns by this thing, and then we're dividing by the resulting determinant and so on. Yes, we could absolutely do that on that point. I am willing, however, to invert this matrix. So 1, 0, minus 1, 2, inverse equals what?
Isn't it the same as row reducing that matrix augmented by the identity matrix?
Yeah, well, we had a formula actually that didn't involve any row reducing. It just involved swapping entries and negating them, dividing by the determinant. Do you remember this one?
Yeah, 1 times 2.
Yeah, we get the determinant, 1 times 2 minus 0. So that'll give me 2. So it's going to be 1/2 times. And then what do we do to the entries?
Not the diagonal and then make the other two negative.
The other two negative. So we get 1, 0, 1/2, 1/2. And then let's sort of pretend I didn't write all this stuff, and I'm just going to treat this as if I just wrote